We built a telescope to see the universe as it was 13 billion years ago, when galaxies were supposed to be young and formless, still gathering themselves from the dark. What the James Webb Space Telescope found instead were structures that looked impossibly mature. Galaxies with the mass and order of systems that should have taken billions of years to form, appearing in an epoch when the universe itself was barely 500 million years old. The light reaching us now suggests something we did not predict, that the early universe was already far more organized than our models allowed for. The James Webb Space Telescope sees in wavelengths the human eye cannot perceive, tuned not to visible light but to infrared radiation, the stretched reddened glow of photons that have traveled across expanding space for billions of years. It is this sensitivity that allows Webb to reach further back in time than any instrument before it, to witness epochs that occurred when the universe was still a fraction of its current age. Light moves at a fixed speed, and because of this constancy, looking outward into space is also looking backward through time. The light from a distant galaxy took billions of years to cross the void between us, and when it finally arrives at our instruments, it carries with it an image of that galaxy, not as it is now, but as it was when that light first began its journey. Webb's infrared capability is crucial because the universe itself is expanding, and as space stretches, it stretches the wavelengths of light traveling through it. Light that left a galaxy in the visible spectrum billions of years ago has been shifted into the infrared by the time it reaches us, a phenomenon known as cosmological redshift. The further away a galaxy is, the more its light has been redshifted, and the earlier in cosmic history it existed. Previous telescopes like Hubble could see far, but their range was limited by their sensitivity to visible and near-infrared light. Webb, with its much larger mirror and instruments designed specifically for deep infrared observation, can detect light from galaxies that formed when the universe was less than 1 billion years old, an era that has remained mostly invisible to us until now. The telescope itself orbits not the Earth, but a point in space nearly 1 million miles away, positioned so that its sun shield, a structure the size of a tennis court, can keep its instruments perpetually cold, shielded from the heat of the sun and Earth. This coldness is essential because infrared light is heat radiation, and to detect faint infrared signals from the distant universe, the telescope must not be contaminated by its own warmth. At this remove from Earth, unimpeded by atmospheric interference or thermal noise, Webb gazes into the cosmic dark with a clarity that allows it to resolve structures in the earliest observable galaxies. It does not merely capture light, it dissects it, breaking incoming photons into spectra that reveal the chemical composition, temperature, and motion of the objects being observed. Every image it produces is the result of hours or days of light gathering. Photons arriving one by one from galaxies so distant that they existed when the universe was 1/10 of its current age. These are not photographs in any familiar sense. They are reconstructions, mosaics of data assembled from infrared wavelengths invisible to us, translated into images we can interpret. What Webb sees is not the universe as it appears now, but as it appeared in deep time, in epochs closer to the beginning than to the present moment. The significance of this capability becomes clear when we consider the scale of cosmic history. The universe is approximately 13.8 billion years old, born from the initial expansion we call the Big Bang. For the first few 100 million years, space was filled with hydrogen and helium gas, slowly cooling and collapsing under gravity into clumps that would eventually ignite as the first stars. These stars, massive and short-lived, flooded the universe with ultraviolet light, ionizing the surrounding gas and seeding space with heavier elements when they exploded. Galaxies formed from the gravitational aggregation of gas, stars, and dark matter, growing over time through mergers and accretion. According to the standard models, this process was gradual. Early galaxies were expected to be small, disordered, and faint, protogalactic fragments still in the process of assembling into larger structures. By the time the universe was a few billion years old, galaxies should have grown into more recognizable forms, with spiral arms, central bulges, and well-defined structures. But Webb is now observing an epoch between 400 million and 800 million years after the Big Bang, a period when the universe was still in its infancy, and what it has found does not align with these expectations. The galaxies Webb has detected in this early era are not small or formless. Some of them appear remarkably massive, with stellar populations comparable to galaxies that formed much later in cosmic history. They show structure, order, and in some cases, signs of mature stellar populations, stars that have already lived and died, enriching their surroundings with heavier elements. The light from these galaxies, stretched and reddened by billions of years of cosmic expansion, reveals objects that should not yet exist in the timeline we had constructed. They are too large, too luminous, too organized for the age of the universe at the time they formed. This is not a matter of a single outlier or a handful of unusual cases. Multiple observations across different regions of the deep sky have returned similar results, suggesting that the phenomenon is widespread, perhaps even typical of that epoch. The question is no longer whether these galaxies exist, but how they came to be so mature so quickly, and what their existence implies about the processes that governed the early universe. The galaxies in question appear in Webb's deepest images as small reddish smudges. Their light so ancient and redshifted that they glow primarily in infrared wavelengths far beyond what the human eye could perceive. To determine their distance, and therefore their age, astronomers measure the degree to which their light has been stretched by cosmic expansion, a value known as redshift, denoted by the letter Z. A galaxy with a redshift of Z equals 1 existed roughly 8 billion years ago, when the universe was about half its current age. A galaxy with a redshift of Z equals 6 existed when the universe was less than 1 billion years old. The galaxies Webb has been observing have redshifts between Z equals 10 and ZR equals 13, placing them in an era between 400 and 600 million years after the Big Bang. At these distances, even large galaxies appear tiny in Webb's images, requiring careful spectroscopic analysis to confirm their properties. The telescope's instruments split the light from these objects into spectra, revealing the characteristic signatures of hydrogen, oxygen, and other elements, as well as the overall energy distribution of their starlight. From these spectra, astronomers can estimate the mass of stars within the galaxy, the rate at which new stars are forming, and the approximate age of the stellar population. What surprises researchers is not merely that galaxies exist at these early times, some small irregular proto-galaxies were expected, but that a number of them have stellar masses comparable to the Milky Way, or even larger. One galaxy observed at a redshift of approximately Z equals 11 appears to contain roughly 100 billion solar masses worth of stars, a figure that places it among the most massive galaxies known at any epoch. Another, detected at Z equals 13, shows signs of having already formed a substantial population of older stars, suggesting that star formation had been ongoing for perhaps 100 million years or more before the light we now observe was emitted. These are not the chaotic, fragmentary structures expected from the earliest phases of galaxy formation. They exhibit organized light distributions, in some cases showing hints of disk-like or bulge-like structures that imply gravitational settling and dynamical maturity. The presence of heavier elements in their spectra, carbon, oxygen, nitrogen, indicates that previous generations of stars had already lived, died, and enriched the gas from which newer stars were forming. This chemical enrichment is a sign of age, of cycles of stellar birth and death that should have taken longer than the time available. The issue is one of timescales. Stars form from collapsing clouds of gas, a process that takes millions of years. Massive stars, which produce the heavy elements detected in these early galaxies, have lifetimes of only a few million years before they explode as supernovae. The gas enriched by these explosions must then cool and recollapse to form new generations of stars. For a galaxy to accumulate 100 billion solar masses of stars, it must convert gas into stars at a prodigious rate over an extended period. Standard models of galaxy formation, which rely on the gradual assembly of matter through gravitational attraction and the hierarchical merging of smaller structures, predict that such massive galaxies should not appear until the universe is several billion years old. The existence of these galaxies at redshifts above Z equals 10 implies that either star formation was far more efficient in the early universe than current models suggest, or that the initial conditions, perhaps the distribution of dark matter, the density of gas, or the intensity of feedback from the first stars, were different in ways we do not yet understand. Dark matter plays a central role in galaxy formation. It is the invisible scaffolding upon which galaxies are built, providing the gravitational wells into which ordinary matter falls. Simulations of cosmic structure formation show that dark matter clumps together first, creating dense halos that attract hydrogen and helium gas. As this gas accumulates, it cools and collapses, eventually forming stars. The process is regulated by feedback mechanisms, stellar winds, supernova explosions, radiation from accreting black holes that can heat the gas and slow or halt star formation. In the early universe, these processes were expected to limit the rate at which galaxies could grow. The presence of massive, mature galaxies so soon after the Big Bang suggests that something about this picture is incomplete. Perhaps dark matter halos formed more rapidly or were denser than predicted. Perhaps the first stars were more massive and produced more heavy elements more quickly. Perhaps the feedback mechanisms that regulate star formation were less effective in the early universe, allowing gas to convert into stars at a higher rate. Or perhaps our understanding of how dark matter itself behaves on these scales is in need of refinement. There is also the possibility that these galaxies are not quite as massive as they appear, that some aspect of their light, perhaps emission from active black holes at their centers or unusual stellar populations, is being misinterpreted in ways that artificially inflate their estimated masses. This is a consideration that astronomers are actively investigating, reanalyzing spectra, and refining models to ensure that the measurements are robust. But even accounting for uncertainties, the general trend remains. The early universe appears to have been more efficient at building large, structured galaxies than our models anticipated, and this efficiency demands an explanation. To speak of the universe at 600 million years old is to speak of an epoch closer to the beginning than to anything we might recognize. The universe today is 13.8 billion years old, and in that span, galaxies have merged and evolved, stars have lived through countless generations, and the large-scale structure of the cosmos, the vast web of filaments and voids that stretches across billions of light-years, has grown from faint density fluctuations into the architecture we observe. 600 million years after the Big Bang, none of this had yet taken shape. The universe was smaller, denser and hotter, though it had already cooled from the initial inferno into a state where atoms could exist and light could travel freely through space. The cosmic microwave background radiation, the afterglow of the Big Bang itself, had already been emitted, its photons beginning their journey across the expanding universe. The first stars had ignited, flooding their surroundings with ultraviolet light and heavy elements, but much of the universe remained dark, filled with neutral hydrogen gas that absorbed light rather than transmitting it. This period, known as the Cosmic Dark Ages, gradually gave way to an era called reionization, when the radiation from early stars and galaxies ionized the hydrogen gas, rendering space transparent once more. The galaxies Webb is observing existed during or just after this transition, in an epoch when the universe was still in the process of becoming illuminated. To place this in perspective, consider that the Earth is 4.5 billion years old. The Sun is 4.5 billion years old. The oldest known stars in the Milky Way are around 13 billion years old, meaning they formed within the first billion years of the universe's existence. When the light now reaching us from these high redshift galaxies was emitted, the universe itself was younger than the oldest stars we can observe in our own galaxy. The Milky Way as we know it did not exist. The solar system would not form for another 9 billion years. Life on Earth would not emerge for more than 12 billion years. These galaxies existed in a cosmos that had not yet built the familiar structures of the present, a cosmos still close to its origin, still assembling the first concentrations of matter that would eventually become the galaxies, stars, and planets we see around us now. And yet within this young universe, some galaxies had already achieved a level of mass and organization that our models predicted should take much longer to develop. The difficulty lies in the nature of gravitational collapse and hierarchical assembly. Structure in the universe grows from the bottom up. Small fluctuations in the density of matter, imprinted during the earliest moments after the Big Bang, serve as seeds for gravitational collapse. Denser regions attract more matter, growing over time into larger and larger clumps. The first objects to form are small, dense halos of dark matter weighing perhaps 1,000,000 times the mass of the Sun, within which the first stars ignite. These small halos merge with one another, forming larger halos, which in turn merge to form larger structures still. Over hundreds of millions of years, this process builds galaxies. The timescale for this growth depends on the density of matter in the universe, the properties of dark matter, and the efficiency with which gas can cool and collapse within dark matter halos. Simulations based on our best understanding of cosmology and galaxy formation predict that the most massive galaxies should not appear until the universe is at least a few billion years old, having assembled through the merging of many smaller predecessors. The presence of massive galaxies at z equals 10 or higher suggests that this timeline was compressed, that the process occurred faster than the simulations anticipated. One possibility is that the initial density fluctuations in the early universe were larger in amplitude than we thought, providing stronger gravitational seeds that could pull matter together more quickly. Another possibility is that dark matter interacts with itself or with ordinary matter in ways that are not accounted for in current models, affecting the rate at which halos collapse. There is also the question of star formation efficiency. How much of the gas within a dark matter halo is converted into stars and how quickly? In present-day galaxies, only a small fraction of the available gas actually forms stars. The rest is either ejected by stellar winds and supernovae or remains in a diffuse hot state that resists collapse. If the early universe had conditions that allowed a much higher fraction of gas to form stars, perhaps because feedback mechanisms were weaker or because the gas was denser and cooled more rapidly, then galaxies could have accumulated stellar mass more quickly than current models predict. The first stars, known as population 3 stars, were likely much more massive than stars forming today, composed almost entirely of hydrogen and helium with no heavy elements to fragment the collapsing gas clouds into smaller pieces. These massive stars would have burned through their fuel in just a few million years, exploding as supernovae and seeding the surrounding gas with the first heavy elements. The second generation of stars, formed from this enriched gas, could have ignited more rapidly, building up stellar populations on shorter timescales. Yet even with these adjustments, the sheer mass and maturity of some of the observed galaxies remain difficult to explain. The challenge is not merely that they are large, but that they appear to have already undergone significant evolution, multiple cycles of star formation, chemical enrichment, and perhaps even mergers with other galaxies. All of this must have occurred within the first few 100 million years of cosmic history, a span that seems barely sufficient for the processes involved. Redshift is the primary tool by which astronomers measure cosmic distance and time, a method rooted in the fundamental nature of light and the expansion of space itself. When light travels through an expanding universe, the wavelengths of that light stretch along with the expansion, shifting toward the red end of the spectrum. This effect is not due to the motion of the galaxy through space in any ordinary sense, but rather to the expansion of space itself, carrying the galaxy away from us. The degree of redshift, how much the light has been stretched, directly correlates with how far the light has traveled, and therefore how long ago it was emitted. A small redshift indicates a relatively nearby galaxy, one whose light has traveled for perhaps a few 100 million years. A large redshift indicates a distant galaxy, one whose light has been traveling for most of the age of the universe. The relationship between redshift and distance is not linear because the expansion rate of the universe has changed over time, but it can be calculated precisely using our understanding of cosmology and the measured properties of the universe's expansion. Astronomers measure redshift by examining the spectra of galaxies, the distribution of light across different wavelengths. Every element emits and absorbs light at characteristic wavelengths, creating a unique spectral fingerprint. Hydrogen, for example, emits a strong line of ultraviolet light at a wavelength of 121.6 nanometers, known as the Lyman alpha line. In a galaxy at rest relative to us, This line would appear at exactly that wavelength. But in a distant, receding galaxy, the expansion of space stretches the light, shifting the Lyman alpha line to longer wavelengths. A galaxy at a redshift of z equals 10, for instance, would have its Lyman alpha line shifted from 121 nanometers in the ultraviolet to approximately 1,330 nanometers in the near-infrared, a stretch of more than tenfold. By identifying these shifted spectral lines and measuring their new wavelengths, astronomers can determine the redshift with great precision, and from that, calculate the distance to the galaxy and the epoch in which it existed. The James Webb Space Telescope excels at this task because its instruments are specifically designed to capture and analyze infrared light. One of its primary instruments, the near-infrared spectrograph, can take the faint light from a distant galaxy and spread it out into a spectrum, revealing the positions of spectral lines with enough clarity to measure redshifts even for extremely faint objects. Another instrument, the near-infrared camera, captures broad images of the sky in multiple infrared wavelengths, allowing astronomers to identify candidate high redshift galaxies based on their colors. Objects that appear bright in longer infrared wavelengths but disappear in shorter ones are likely to be at very high redshifts. Their light shifted entirely out of the visible and into the infrared. Once candidates are identified, follow-up spectroscopy confirms their distances. This process has allowed Webb to compile a growing catalogue of galaxies at redshifts above z equals 10, each one a window into the universe as it existed in its first billion years. The precision of these measurements is remarkable. Redshift values can be determined to within a few percent, and in some cases to within a fraction of a percent, allowing astronomers to place galaxies at specific moments in cosmic history with considerable confidence. A galaxy at z equals 11 existed approximately 420 million years after the Big Bang. A galaxy at z equals 13 existed approximately 330 million years after the Big Bang. These are not rough estimates, but carefully derived values based on well-understood physics and observational data. The uncertainty lies not in the redshift measurements themselves, but in the interpretation of what those galaxies were like, their masses, their star formation rates, the ages of their stellar populations. These quantities must be inferred from the light we observe, using models of stellar evolution, dust absorption, and the spectral signatures of different types of stars. It is here, in the modeling, that the surprises have emerged. When astronomers fit models to the spectra of these high redshift galaxies, attempting to match the observed light with predictions based on stellar populations of various ages and compositions, they find that the best fits often require large stellar masses and, in some cases, surprisingly old stars. A galaxy observed at z equals 12, for instance, might show spectral features consistent with a stellar population that is already 100 million years old, meaning that stars had been forming in that galaxy since z equals 15 or higher, an epoch only 200 million years after the Big Bang. The light from these older stars contributes to the overall spectrum in ways that distinguish them from younger, hotter stars, and the presence of heavy elements in the spectrum, lines of oxygen, carbon, and iron, confirms that previous generations of stars had already lived and died. The models are not perfect, and there are degeneracies. Different combinations of stellar age, mass, and dust content can sometimes produce similar spectra, but the general conclusion remains robust. These galaxies are more mature than expected for their epoch. The discovery is not a single observation, but a pattern emerging from multiple independent measurements across different regions of the sky, observed at different times, analyzed by different research teams. The consistency of the findings lends them weight, suggesting that what Webb is revealing is not an anomaly, but a characteristic feature of the early universe. The standard model of galaxy formation, built over decades of observation, simulation, and theoretical work, describes a universe in which structure emerges gradually through the gravitational amplification of tiny density variations. In the very early universe, moments after the Big Bang, quantum fluctuations were stretched by cosmic inflation into macroscopic variations in the density of matter. These variations were small, on the order of 1 part in 100,000, but they were enough to seed the eventual formation of all cosmic structure. Regions that were slightly denser than average exerted slightly stronger gravitational pull, attracting more matter from their surroundings. Over time, these overdense regions grew, pulling in more and more material, while underdense regions became voids, emptied of matter by the gravitational attraction of their denser neighbors. This process, driven entirely by gravity, is known as gravitational instability, and it is the engine of structure formation in the universe. Dark matter, which makes up approximately 85% of the matter in the universe, plays the dominant role in this process because it interacts only through gravity, unaffected by radiation pressure or electromagnetic forces that can slow the collapse of ordinary matter. Dark matter clumps together first, forming halos, roughly spherical concentrations of mass, that serve as gravitational wells into which ordinary matter, primarily hydrogen and helium gas, subsequently falls. As the gas falls into these dark matter halos, it collides with other infalling gas, heats up and radiates energy, allowing it to cool and settle into a rotating disk at the center of the halo. Once the gas is sufficiently dense and cool, it fragments into clouds that collapse under their own gravity, eventually igniting as stars. This process does not happen all at once. In the hierarchical model of structure formation, small halos form first, and larger structures are built through the merging of these smaller units. A massive galaxy like the Milky Way is understood to have formed through the gradual accumulation and merging of hundreds or thousands of smaller galaxies over billions of years. Evidence for this process can be seen in the stellar streams and dwarf satellite galaxies that surround the Milky Way, remnants of smaller systems that have been or are being absorbed. The rate at which galaxies grow is governed not only by the availability of gas and the efficiency of star formation, but also by feedback processes that regulate and sometimes halt the conversion of gas into stars. When massive stars explode as supernovae, they inject enormous amounts of energy into the surrounding gas, heating it and driving it outward in powerful winds. This heated gas can be expelled from the galaxy entirely, or it can be rendered too hot to collapse and form new stars, effectively shutting down star formation for a period of time. Similarly, supermassive black holes at the centers of galaxies, as they accrete matter, release tremendous amounts of energy in the form of radiation and jets, which can also heat and expel gas. These feedback mechanisms are thought to be crucial in preventing galaxies from converting all their available gas into stars too quickly. Without feedback, simulations predict that galaxies would be far more massive and would have exhausted their gas supplies much earlier than observations suggest. The balance between infill star formation and feedback is delicate, and it determines the final mass, size, and structure of a galaxy. In the early universe, the expectation was that this process would be slower and less efficient. The first dark matter halos to collapse were small, with masses perhaps 1 million times that of the Sun, capable of hosting only a few stars. These halos would merge over time, forming larger halos that could trap more gas and form more stars. But the process of merging takes time. Halos must encounter one another, a process governed by the large-scale distribution of matter and the dynamics of gravitational attraction. Once halos merge, their gas must settle into a new equilibrium, cool, and collapse again before forming stars. Each step in this sequence requires tens or hundreds of millions of years. The first galaxies, therefore, were expected to be small and irregular, with stellar masses perhaps a few million to a few billion times the mass of the Sun. Over the next several billion years, as more and more halos merged and as continuous star formation built up stellar populations, galaxies would gradually grow into the massive, structured systems we observe in the later universe. The most massive galaxies, those with stellar masses exceeding 100 billion solar masses, were expected to appear only after the universe was several billion years old, once sufficient time had passed for hierarchical assembly to build up such large structures. The galaxies Webb is observing do not fit this timeline. They appear too massive and too mature for the age of the universe at the time they existed, suggesting that either the hierarchical assembly process was faster than models predict, or that some other mechanism was at play, allowing these galaxies to accumulate mass more efficiently. One possibility is that the initial density fluctuations in certain regions of the early universe were higher than average, providing stronger gravitational seeds that could pull matter together more rapidly. Another possibility is that star formation in the early universe was simply much more efficient, converting a larger fraction of available gas into stars before feedback processes could expel or heat the gas. Yet another possibility is that these early galaxies formed not through the gradual merging of smaller halos, but through the direct collapse of massive gas clouds in particularly dense regions, a process that would bypass some of the slower steps of hierarchical assembly. Each of these scenarios has implications for our understanding of dark matter, star formation, and the initial conditions of the universe, and distinguishing between them requires additional observations and more detailed modeling. When Webb turns its instruments toward a patch of seemingly empty sky and gathers light for hours or days, the resulting image reveals thousands of galaxies, each one a distinct smudge of light against the darkness. Most of these galaxies are relatively nearby in cosmic terms, their light having traveled for a few billion years or less, and they appear as structured systems with spiral arms, elliptical shapes, or irregular forms. But among them, appearing as tiny reddish dots, are the high redshift galaxies, objects so distant that their light has been traveling for more than 13 billion years, emitted when the universe was in its infancy. These galaxies are small in angular size, often spanning just a few pixels in Webb's images, but their colors distinguish them. They are brightest in the longest infrared wavelengths and dim or invisible in shorter wavelengths, a signature of extreme redshift. Their light, originally emitted in the ultraviolet and visible spectrum, has been stretched into the infrared by the expansion of space, and the characteristic spectral features that astronomers use to identify them, emission lines from hydrogen, oxygen, and other elements, have been shifted accordingly. The physical appearance of these galaxies, even at the resolution Webb provides, is difficult to discern in detail. They are compact, with light concentrated in small regions, suggesting that their stars are packed into relatively dense configurations. Some show hints of elongation or asymmetry, which might indicate irregular shapes or ongoing mergers with other small galaxies. Others appear more centrally concentrated, with light distributions that could be consistent with early bulges or dense stellar cores. The resolution is limited not by the telescope's capability, but by the sheer distance involved. These galaxies are so far away that even Webb's sharp vision cannot resolve individual star-forming regions or spiral structures if such features exist. What can be measured, however, is the total brightness of the galaxy across different wavelengths, and from this brightness, combined with spectroscopic data, astronomers can infer a great deal about the galaxy's properties. The spectra of these galaxies are rich with information. Strong emission lines from ionized oxygen, hydrogen, and other elements indicate active star formation, young, massive stars producing intense ultraviolet radiation that ionizes the surrounding gas, causing it to glow. The strength of these emission lines relative to the underlying continuum of starlight provides clues about the rate at which stars are forming. In some of these early galaxies, the inferred star formation rates are remarkably high, on the order of tens or even hundreds of solar masses per year. For comparison, the Milky Way currently forms stars at a rate of about 1 to 2 solar masses per year. The presence of strong emission lines also confirms that the gas in these galaxies has been enriched with heavy elements, oxygen and carbon produced by previous generations of stars. The relative strengths of different emission lines can be used to estimate the metallicity of the gas, the fraction of elements heavier than helium, and in some cases, these early galaxies show metallicities that are a few % of the solar value, which is surprisingly high for objects existing so early in cosmic history. Beneath the emission lines lies a continuum of light produced by the cumulative glow of billions of stars. The shape of this continuum, how bright the galaxy is at different wavelengths, depends on the types of stars present and their ages. Young, massive stars emit most of their light in the ultraviolet and blue parts of the spectrum, while older, lower-mass stars emit more light in the red and infrared. By fitting models of stellar populations to the observed continuum, astronomers can estimate the total stellar mass of the galaxy, and the average age of its stars. This is where the surprises have been most pronounced. For several of the massive galaxies observed at redshifts above Z equals 10, the best-fit models suggest stellar masses in the range of 10 billion to 100 billion solar masses, comparable to or even exceeding the stellar mass of the Milky Way. Some of these models also indicate the presence of older stellar populations, stars that are not actively forming, but have already passed through their main sequence lifetimes, contributing to the overall light in ways that suggest they formed several hundred million years earlier. If these interpretations are correct, it means that star formation in these galaxies began at redshifts of 15 or higher, when the universe was less than 300 million years old. The uncertainty in these measurements is not negligible. The models used to infer stellar masses and ages rely on assumptions about the initial mass function of stars, the distribution of stellar masses at birth, and the history of star formation within the galaxy. Different assumptions can lead to different estimates. Dust within the galaxy can absorb and scatter light, altering the observed spectrum in ways that might be mistaken for older stellar populations. Active galactic nuclei, powered by supermassive black holes accreting matter at the centers of galaxies, can contribute additional light that complicates the interpretation. Researchers are working to refine these models, to explore the full range of possibilities, and to identify which scenarios are most consistent with the data. But even after accounting for these uncertainties, the general finding remains. The early universe contained galaxies that were more massive and more evolved than standard models predicted, and this discrepancy is not easily explained away. The tension between observation and theory is not a contradiction in the sense of one being wrong and the other right, but rather a signal that our understanding is incomplete, that the models we have constructed to explain the universe are approximations that work well in some regimes, but require refinement or revision when applied to others. Scientific models are tools, built from observations, mathematical frameworks, and physical principles, designed to predict how systems behave under various conditions. When a model successfully predicts observations, it gains credibility and becomes part of the accepted framework. When observations deviate from predictions, it indicates that the model is missing something, a physical process, an initial condition, a parameter value that matters in the context being studied. The discovery of unexpectedly massive galaxies in the early universe is an observation of this kind, one that does not invalidate the entire framework of cosmology and galaxy formation, but suggests that certain aspects of that framework need adjustment. The hierarchical model of galaxy formation, for instance, is built on solid foundations. It is grounded in the theory of gravitational instability, which has been tested and confirmed across a wide range of scales and epochs. The large-scale structure of the universe, the distribution of galaxies into filaments and clusters separated by vast voids, matches the predictions of simulations based on gravitational collapse and dark matter. The cosmic microwave background radiation, observed in exquisite detail by satellites like Planck, provides a snapshot of the density fluctuations in the early universe, and these fluctuations serve as the initial conditions for structure formation. When those initial conditions are fed into simulations that follow the evolution of dark matter and gas over billions of years, the resulting structures closely resemble the universe we observe today. The hierarchical model has been successful in explaining the properties of galaxies at redshifts below Z equals 6, an epoch spanning the last 12 billion years of cosmic history. But the very early universe, the first billion years, is a regime that has been less thoroughly tested, simply because until recently we lacked the instruments to observe it in detail. Webb is now providing that detail, and the observations are revealing aspects of the early universe that were not anticipated by the models. One of the key questions is whether the discrepancy lies in our understanding of the initial conditions, the physical processes, or both. The initial density fluctuations imprinted by inflation are thought to follow a specific statistical distribution, characterized by their amplitude and scale dependence. If the amplitude of these fluctuations was slightly higher than current measurements suggest, particularly on the scales corresponding to galaxy formation, it would mean that the seeds for structure formation were stronger, allowing matter to collapse more quickly into larger halos. This could shorten the timescale for galaxy assembly, allowing massive galaxies to form earlier than current models predict. However, the amplitude of these fluctuations is tightly constrained by observations of the cosmic microwave background, and any significant increase would have other observable consequences that are not seen. This makes it unlikely that a simple adjustment to the initial conditions alone can fully explain the observations. Alternatively, the issue might lie in the efficiency of star formation and the role of feedback. In simulations, the fraction of gas that converts into stars within a dark matter halo is typically assumed to be relatively low, on the order of 10 to 20%, with the rest either remaining as diffuse gas or being expelled by feedback from supernovae and active galactic nuclei. This assumption is based on observations of galaxies in the later universe, where feedback mechanisms are well documented and appear to be effective at regulating star formation. But in the early universe, conditions were different. The gas was denser, the dark matter halos were smaller and more concentrated, and the first generations of stars were likely more massive and shorter-lived than stars today. It is possible that in this environment, feedback was less effective at expelling gas, allowing a much higher fraction of the available gas to form stars before feedback could halt the process. If star formation efficiency in the early universe was 2 or 3 times higher than currently assumed, it would allow galaxies to accumulate stellar mass more rapidly, potentially explaining the presence of massive galaxies at high redshifts. There is also the question of dark matter itself. The standard model assumes that dark matter is cold. That is, it consists of particles moving at non-relativistic speeds, which allows it to clump together on small scales and form the dense halos needed for galaxy formation. If dark matter has properties that differ slightly from this standard picture, if it interacts with itself through forces other than gravity, or if it has a small but non-zero velocity dispersion, it could affect the rate at which halos collapse and merge, altering the timeline of galaxy formation. These alternative dark matter models are constrained by many observations, but there remains some parameter space that has not been fully explored, and it is conceivable that subtle differences in dark matter properties could have measurable effects on the formation of the earliest galaxies. Another possibility is that the early universe underwent a period of enhanced structure formation due to processes that are not included in current models. For example, if primordial magnetic fields were present in the early universe, they could have affected the cooling and collapse of gas in ways that are not accounted for in standard simulations. Or, if there were slight variations in the properties of dark energy or the expansion rate of the universe in the very early epochs, they could have influenced the growth of structure. These are speculative ideas, not yet supported by direct evidence, but they illustrate the range of possibilities that researchers are considering as they work to reconcile the observations with theory. What is clear is that the observations are robust and that they demand an explanation, one that will likely involve a combination of refined initial conditions, improved modeling of star formation and feedback, and perhaps new insights into the nature of dark matter or the physical conditions of the early universe. The light arriving at Webb's mirrors tonight left those distant galaxies when the universe was young, and it has been traveling ever since, moving through expanding space at the fixed speed that light always travels, never slowing, never stopping. Photons emitted by stars that may no longer exist, from galaxies that have since merged with others or evolved beyond recognition, cross the void for 13 billion years before reaching the telescope's gold-coated beryllium surface, where they are gathered, focused, and transformed into data. This is not an instantaneous process. Webb observes a single patch of sky for extended periods, sometimes for hundreds of hours, allowing photons to accumulate one by one until enough have been collected to form an image or a spectrum with sufficient clarity to be analyzed. The faintest galaxies in Webb's images are detected by perhaps a few dozen photons total, gathered over days of observation, each photon a messenger from an epoch so distant that the journey it has completed spans nearly the entire history of the cosmos. To observe the early universe is to observe not just a different time but a different state of existence. The universe, at 600 million years old, was not simply a younger version of the present universe with fewer galaxies and less structure. It was denser, hotter, and smaller by a factor of 10 or more in linear dimensions, meaning that the average distance between galaxies was much shorter, and the likelihood of interactions and mergers was correspondingly higher. The cosmic microwave background radiation, now cooled to a temperature of just under 3 degrees above absolute zero, was then at a temperature of 30 degrees, still frigid but warm enough to have perceptible thermal effects on the gas filling the universe. The expansion rate of the universe was faster. Space was stretching more rapidly than it does today, driven by the higher density of matter and energy present at that time. The wavelength of light itself was shorter, squeezed by the smaller scale of space, and what we now observe as infrared emission was originally emitted as ultraviolet or visible light, stretched over billions of years into the wavelengths we detect today. In this young universe, the first galaxies existed in close proximity to one another, separated by distances of only a few million light-years, rather than the tens or hundreds of millions of light-years that separate galaxies today. They moved through a cosmic environment that was still transitioning from the dark ages to the epoch of reionization, a period when the ultraviolet radiation from the first stars and galaxies was gradually ionizing the neutral hydrogen gas that filled space, rendering it transparent to light. Before reionization, the universe was foggy, filled with neutral hydrogen that absorbed ultraviolet photons and scattered them in random directions, preventing light from traveling freely across large distances. As more and more stars ignited and more galaxies formed, the cumulative radiation from these sources ionized the hydrogen, creating expanding bubbles of ionized gas around each galaxy. These bubbles eventually overlapped and merged, until by around 1 billion years after the Big Bang, the entire universe had been reionized, and space became transparent as it is today. The galaxies Webb is observing existed during or shortly after this transition, in an era when the universe was just becoming illuminated by the light of its first luminous structures. The stars within these early galaxies were not like the Sun. They formed from gas that was nearly pristine, composed almost entirely of hydrogen and helium, with only trace amounts of heavier elements. The first stars, those of the so-called population 3, contained no metals at all, metals being the term astronomers use to describe all elements heavier than helium. These first stars were likely extremely massive, perhaps tens or even hundreds of times the mass of the Sun, and they burned through their nuclear fuel in just a few million years, ending their lives in violent supernova explosions that seeded the surrounding gas with the first carbon, oxygen, nitrogen, and iron. The second generation of stars, formed from gas enriched by these supernovae, could be less massive and longer lived, but they still formed in an environment quite different from the present-day universe. The lack of heavy elements meant that the gas could not cool as efficiently as it does in the present-day interstellar medium, where metals facilitate cooling through emission lines. This likely affected the mass distribution of stars, favoring more massive stars in the early universe than are typical today. These massive stars produced copious amounts of ultraviolet radiation, ionizing their surroundings and contributing to the reionization of the universe, but they also lived brief lives, leaving behind neutron stars and black holes that would become the seeds for future generations of compact objects. The galaxies we observe at high redshifts are not isolated systems, but participants in a larger cosmic web, connected to their surroundings by streams of gas and dark matter flowing along filaments of the large-scale structure. Even in the early universe, structure was not uniformly distributed. Some regions were denser than others, and it was in these overdense regions that galaxies formed most rapidly, clustering together in protogroups that would eventually evolve into the galaxy clusters we observe in the later universe. The galaxies Webb has detected are likely located in such overdense regions, which would help explain their rapid growth. They had access to more gas, more dark matter, and more opportunities for mergers than galaxies forming in average density regions. Understanding the environments in which these early massive galaxies formed is an active area of research, requiring not just observations of individual galaxies, but also studies of the large-scale structure and the distribution of matter around them. Researchers are exploring multiple pathways that might explain how galaxies could have assembled so much mass so quickly in the early universe, each pathway grounded in physics, but extending beyond what the standard models currently predict. One avenue of investigation focuses on the properties of dark matter, halos in the very early universe, particularly whether these halos could have been denser or more concentrated than simulations typically predict, providing stronger gravitational wells that could pull in and retain gas more effectively. Dark matter halos grow through the merging of smaller halos, but the rate at which this happens depends on the local density of dark matter and the initial clustering of matter. If the regions where these early massive galaxies formed were significantly overdense, more so than typical regions at that epoch, they would have experienced accelerated halo growth, with more frequent mergers bringing more mass together in shorter timescales. This could create unusually massive dark matter halos early on, capable of hosting correspondingly massive galaxies. Another possibility involves the direct collapse of massive gas clouds into galaxies without going through the slower process of hierarchical assembly. In standard scenarios, small halos form first and then merge to build larger structures, but under certain conditions, a sufficiently dense cloud of gas could collapse directly into a large halo, bypassing the intermediate steps. This process, known as direct collapse, requires specific conditions. The gas must be able to cool and collapse without fragmenting into smaller pieces, which typically requires either very high densities or the presence of molecular hydrogen to facilitate cooling. In the very early universe, before the first stars had formed and before metals were present, molecular hydrogen was the primary coolant, and regions with high concentrations of molecular hydrogen could have undergone rapid, monolithic collapse, forming large structures much faster than hierarchical assembly would allow. If some fraction of the massive early galaxies formed through direct collapse rather than through mergers, it would help explain their presence at such high redshifts. Star formation efficiency is another critical variable. In present-day galaxies, only a small fraction of the available gas actually forms stars, with the rest either remaining diffuse or being expelled by feedback processes. But in the early universe, several factors might have allowed for much higher star formation efficiency. The gas was denser, having been compressed by the smaller scale of the universe, which would have made it easier for gravitational collapse to overcome internal pressure and fragment into star-forming clouds. The lack of heavy elements meant that there were fewer dust grains to absorb and re-radiate energy, which in the present-day universe helps regulate the temperature and pressure of the interstellar medium. Without this regulation, gas in the early universe might have collapsed more readily and formed stars more rapidly. Additionally, feedback processes might have been less effective at expelling gas from early galaxies. Supernova explosions inject energy into the surrounding medium, but whether this energy is sufficient to unbind the gas from the galaxy's gravitational potential depends on the depth of that potential well and the distribution of the gas. In dense, compact early galaxies with deep potential wells, feedback might have been less effective at driving gas out, allowing star formation to continue at high rates for longer periods. There is also the question of whether the initial mass function of stars, the distribution of stellar masses at birth, was different in the early universe than it is today. In the present-day universe, star formation produces a mix of masses, with most stars being relatively low mass, like the Sun or smaller, and only a small fraction being massive stars. This distribution has been measured in nearby star-forming regions and appears to be relatively universal, but it is based on observations of stars forming from gas that has already been enriched with metals. In the pristine environment of the early universe, where gas contained almost no heavy elements, the physical processes governing fragmentation and collapse might have been different, potentially favoring the formation of more massive stars. If the early universe produced a higher proportion of massive stars, this would have several consequences. Massive stars are much more luminous than low-mass stars, so a galaxy with a top-heavy initial mass function would appear brighter and might be mistaken for a galaxy with more total stellar mass than it actually contains. Massive stars also produce more heavy elements and inject more energy into their surroundings, accelerating the chemical enrichment of the galaxy and potentially affecting the subsequent generations of star formation. A top-heavy initial mass function would also mean that much of the stellar mass formed in the early universe would have already disappeared, having lived out its brief life and collapsed into neutron stars or black holes, leaving behind remnants that contribute to the total mass but do not emit light. Each of these possibilities, overdense environments, direct collapse, enhanced star formation efficiency, different initial mass functions, represents a potential piece of the puzzle, and it is likely that the full explanation involves some combination of them rather than a single dominant factor. The challenge for researchers is to determine which of these processes were most important and under what conditions, and to incorporate these insights into updated models that can reproduce the observations. This requires not only refining the models themselves, but also obtaining additional observations that can test specific predictions and distinguish between different scenarios. Scientific models are not fixed truths, but evolving frameworks, constructed to organize our understanding of phenomena and to make predictions that can be tested against observation. When a model successfully predicts something that has not yet been observed, it gains credibility and suggests that the underlying assumptions are capturing something real about the way nature works. When observations diverge from predictions, it does not necessarily mean the model is fundamentally wrong, but rather that it is incomplete, that it describes certain aspects of reality accurately while missing others. The history of astronomy is filled with such moments, instances when new observations revealed phenomena that existing models could not explain, prompting refinement, revision, and sometimes wholesale rethinking of the frameworks that had seemed secure. The discovery of the accelerating expansion of the universe in the late 1990s, for instance, was not predicted by the models of cosmology at the time, which assumed that the expansion should be slowing down under the influence of gravity. The observation of distant supernovae appearing dimmer than expected forced cosmologists to introduce the concept of dark energy, a component of the universe that exerts a repulsive effect, driving the acceleration. This was not a failure of cosmology, but an expansion of it, an acknowledgement that the universe contains elements that had not been anticipated. The current tension between Webb's observations and the standard model of galaxy formation is of a similar nature. It does not overturn the entire structure of cosmological theory. The evidence for dark matter, the expansion of the universe, the formation of structure through gravitational collapse, all of this remains well supported by a vast body of observations. What it does suggest is that our understanding of the details, particularly the processes governing the earliest phases of galaxy formation, is not yet complete. This is not surprising. The early universe is a regime that has been difficult to observe until recently, and the physical conditions in that epoch, extreme densities, rapid expansion, the dominance of pristine gas, and the first generations of stars, are different enough from later epochs that extrapolating models backward in time involves uncertainties. The discovery of massive early galaxies is a prompt to revisit those extrapolations, to test assumptions that may have seemed reasonable in the absence of data, but that now require adjustment in light of what we are seeing. The process of refining models in response to new observations is careful and deliberate. It involves revisiting the simulations, adjusting parameters, testing different physical assumptions, and comparing the results with the full range of available data, not just the new observations, but also older observations that the models were originally designed to explain. A model that successfully explains the presence of massive galaxies at high redshifts, but fails to reproduce the properties of galaxies at lower redshifts, or that predicts other observable consequences that are not seen, would not be considered viable. The goal is to find a framework that is consistent with all observations across all epochs, and this requires balancing competing constraints. Researchers are running new simulations with higher resolution, incorporating more detailed models of star formation and feedback, exploring different assumptions about dark matter and the initial conditions, and comparing the outputs with Webb's observations to see which scenarios come closest to matching what is seen. This work is being carried out by many groups around the world, each bringing different expertise and different approaches. Some focus on the theoretical side, developing models and running simulations. Others focus on the observational side, analyzing Webb's data, measuring redshifts and spectral properties, and compiling catalogues of high redshift galaxies. Still others work on interpreting the observations in light of theory, fitting models to the data, and assessing which physical scenarios are most consistent with the measurements. The process is collaborative and iterative, with findings shared through papers, conferences, and informal discussions, and with each new result informing the next steps. It is also necessarily slow, not because the researchers lack urgency, but because the questions are complex and the data require careful analysis. A spectrum from a distant galaxy might take months to fully interpret, with researchers exploring different models, testing for systematic errors, and checking their conclusions against independent measurements. The stakes are high, not in the sense of proving one side right and another wrong, but in the sense that the answers will shape our understanding of how the universe came to be the way it is. What is emerging from this work is not a single definitive answer, but a range of possibilities, each with its own implications and each requiring further testing. Some researchers emphasize the potential role of enhanced star formation efficiency in the early universe, pointing to simulations that show higher conversion rates of gas into stars when feedback is less effective. Others focus on the possibility that the initial density fluctuations were larger than expected in certain regions, providing the seeds for rapid structure formation. Still others explore the idea that the early universe might have been more conducive to direct collapse scenarios, allowing massive galaxies to form through monolithic collapse rather than hierarchical assembly. These are not mutually exclusive explanations, and it is likely that different mechanisms contributed in different contexts, with some galaxies forming through one pathway and others through another. There is a particular kind of intellectual humility that comes from confronting the universe with instruments capable of revealing what was previously invisible. A recognition that our understanding is always provisional, always subject to revision in light of new evidence. Before the Hubble Space Telescope was launched in 1990, the expansion rate of the universe was known only to within a factor of 2. Estimates ranged from 50 to 100 kilometers per second per megaparsec, an uncertainty that translated into fundamental ambiguity about the age and size of the universe. Hubble's observations of distant supernovae and Cepheid variable stars narrowed this range dramatically, establishing the expansion rate with a precision that had not been possible before, and in doing so, it reshaped our understanding of cosmic history. Before that, in the 1920s, Edwin Hubble's observation that galaxies were receding from us at speeds proportional to their distances overturned the prevailing view of a static universe and revealed that space itself was expanding, a discovery that led to the development of the Big Bang theory. Each of these moments represents an instance when observation pushed beyond the boundaries of what theory anticipated, requiring not the abandonment of previous knowledge, but its integration into a larger framework that could accommodate the new findings. The James Webb Space Telescope is operating in this same tradition, extending our observational reach into regimes that were previously inaccessible, and in doing so, uncovering aspects of the universe that our models had not fully captured. The discovery of massive early galaxies is not the overthrow of cosmology, but a refinement of it, a signal that the early universe was more complex, more efficient, or more varied in its behavior than we had assumed based on observations of later epochs. This is how science advances, not through the wholesale rejection of previous frameworks, but through the gradual accumulation of observations that test, constrain, and ultimately improve our models. The standard model of cosmology, built on decades of observations and theoretical work, remains robust in its broad outlines. The universe began in a hot, dense state approximately 13.8 billion years ago. It has been expanding and cooling ever since. Structure formed through the gravitational collapse of dark matter and ordinary matter, with galaxies, stars, and planets emerging from the primordial density fluctuations imprinted in the early universe. All of this is well established and supported by multiple independent lines of evidence. What Webb is revealing is not that this picture is wrong, but that the details, the timescales, the efficiencies, the pathways by which structure formed, are more nuanced than the models had suggested. The researchers working with Webb's data are acutely aware of this. They approach the observations with both excitement and caution, recognizing that the findings are significant, but also that they must be interpreted carefully with attention to potential sources of error and alternative explanations. When a spectrum is analyzed and a galaxy is determined to have a redshift of Z equals 12 and a stellar mass of 50 billion solar masses, the researchers do not simply announce the result and move on. They check the calibration of the instruments, examine the quality of the data, fit multiple models to the spectrum to see how sensitive the conclusions are to different assumptions, compare the result with other observations of similar galaxies, and publish their findings along with detailed descriptions of the methodology and the uncertainties. This process of verification and cross-checking is essential to the practice of science, and it is through this process that confidence in the findings gradually builds. When multiple independent teams, using different methods and different datasets, arrive at similar conclusions, the weight of evidence becomes compelling. At the same time, the researchers are mindful that early observations from a new instrument can sometimes be misleading, particularly when the phenomena being observed are at the edge of the instrument's capabilities. Webb is extraordinarily sensitive and capable, but it is still subject to limitations: instrumental noise, calibration uncertainties, the challenges of disentangling faint signals from background light. Some of the early candidate high redshift galaxies identified by Webb have turned out upon further analysis to be lower redshift galaxies with unusual spectral properties, or to be contaminated by foreground objects. This is a normal part of the observational process, and it underscores the importance of follow-up observations and careful analysis. The galaxies that have been confirmed through spectroscopy, with well-measured redshifts and robust estimates of their properties, are the ones that drive the current discussion, and even these require continued scrutiny as more data become available and as models are refined. The broader scientific community is responding to these findings with a mixture of interest, skepticism, and active investigation. Some researchers are focusing on the observational side, working to expand the sample of high redshift galaxies, to measure their properties with greater precision, and to explore whether there are systematic effects that might be affecting the interpretations. Others are focusing on the theoretical side, developing new models, running new simulations, and exploring which physical scenarios can best explain the observations. Still others are working to connect the observations to other areas of cosmology and astrophysics, considering what the presence of massive early galaxies might imply for the history of ionization, the growth of supermassive black holes, the chemical enrichment of the universe, and the formation of the cosmic web. The findings are prompting a re-evaluation not just of galaxy formation models, but of our broader understanding of the first billion years of cosmic history, a period that is now being illuminated in unprecedented detail. What is clear is that the early universe was not a simple, uniform environment, but a complex, dynamic epoch in which multiple processes operated simultaneously, each contributing to the emergence of structure in ways that are still being disentangled, and that the presence of massive galaxies so early in cosmic time is a clue, a signpost pointing toward aspects of this epoch that we are only beginning to understand. There have been other moments in the history of astronomy when observations revealed a universe stranger and more complex than the prevailing models allowed. In the early 20th century, measurements of stellar distances using Cepheid variables showed that certain nebulae were far too distant to be part of our own galaxy, revealing that what had been thought to be a single cosmic structure was in fact just one of countless galaxies scattered throughout an immense universe. This discovery, made possible by the resolving power of new telescopes and the systematic work of astronomers like Henrietta Swan Leavitt and Edwin Hubble, fundamentally altered humanity's conception of its place in the cosmos, transforming the scale of the known universe almost overnight. The models that had described a single, static galaxy containing all that existed had to be abandoned in favor of a dynamic, expanding cosmos filled with billions of galaxies, each separated from the others by vast distances. The adjustment was not immediate. There was debate, skepticism, and careful verification, but ultimately the observations were too clear to dismiss, and the framework shifted to accommodate them. Decades later, observations of the rotation speeds of spiral galaxies revealed another anomaly, Stars at the outer edges of galaxies were moving faster than could be explained by the visible mass of stars and gas within those galaxies. According to Newton's laws of gravity, stars farther from the galactic center should orbit more slowly, just as planets farther from the Sun orbit more slowly. But the observations showed that rotation speeds remained roughly constant even at large distances from the center, implying that there was far more mass present than could be accounted for by the luminous matter alone. This discrepancy led to the hypothesis of dark matter, an unseen component that dominates the mass of galaxies and provides the additional gravitational pull needed to explain the observed rotation curves. The existence of dark matter was initially controversial, but as more evidence accumulated from gravitational lensing, galaxy clusters, and the structure of the cosmic microwave background, it became clear that dark matter was not only real, but constituted the majority of the matter in the universe. The models of galaxy formation and cosmology were revised to incorporate this invisible component, and our understanding of the universe's composition shifted dramatically with ordinary matter, the atoms that make up stars, planets, and everything we can directly observe, representing only a small fraction of the total. These historical episodes share a common pattern. A well-established model, built on the best available data and LIRON, successfully explains a wide range of phenomena and gains acceptance within the scientific community. New observations, made possible by advances in technology or methodology, reveal phenomena that the model cannot easily accommodate. Initially, there is an attempt to explain the discrepancy within the existing framework, to see if small adjustments or overlooked effects can resolve the tension. When these attempts prove insufficient, the model is revised or extended, incorporating new elements that were not part of the original formulation. The revised model is tested against additional observations, and if it successfully explains both the old data and the new, it gradually replaces the previous version. This process is not instantaneous. It can take years or even decades for a new paradigm to become fully established, but it is driven by the accumulation of evidence and the rigor of scientific method, not by consensus or authority. The discovery of massive galaxies in the early universe by the James Webb Space Telescope fits within this pattern. The standard model of galaxy formation, built on gravitational collapse, dark matter halos, and hierarchical assembly, has been successful in explaining the properties of galaxies across a wide range of redshifts and environments. But Webb's observations of the highest redshift galaxies reveal structures that appear too massive and too mature for the timescales predicted by the model. This is not yet at the level of the discoveries that revealed the expansion of the universe or the existence of dark matter. Those were paradigm-shifting findings that required the introduction of entirely new concepts. The current situation is more subtle, a discrepancy in the details rather than the broad framework, but it is nonetheless significant. It suggests that our models of the early universe, which have been extrapolated backward from observations of later epochs, are missing something, a process, a parameter, a condition that matters in the first few 100 million years after the Big Bang. History suggests that such discrepancies are often resolved through a combination of refined observations and improved models. Sometimes the initial interpretation of the observations turns out to be incorrect, a systematic error, a misidentification, an overlooked effect, and the discrepancy disappears with better data. Other times, the observations are robust and the models must be adjusted to accommodate them, and occasionally the resolution requires the introduction of a genuinely new idea, a concept that had not been part of the previous framework. At this point in the investigation of Webb's findings, all of these possibilities remain open. The observations are being scrutinized, the models are being refined, and new ideas are being explored, all in an effort to understand what the early universe was really like and how it produced the structures we now see. The universe at high redshift is not a place we can visit, not an environment we can probe with instruments sent across space. It exists only as light, as information encoded in photons that have traveled for billions of years to reach us, carrying with them an image of what was, not what is. The galaxies we observe at z equals 12 no longer look the way they did when that light was emitted. They have continued to evolve, merging with other galaxies, forming new generations of stars, perhaps transforming into structures entirely unlike their early configurations. Some may have become massive elliptical galaxies, their star formation long since quenched, their stellar populations old and red. Others may have merged into even larger systems, contributing their stars and gas to structures that now span hundreds of thousands of light years. A few may have remained relatively isolated, evolving more slowly, but even these would bear little resemblance to their appearance 13 billion years ago. The light we observe is a record of a moment that has passed, a snapshot of a galaxy, frozen at an early stage of its existence, while the galaxy itself has moved forward through billions of years of cosmic time that we cannot observe. This temporal displacement is fundamental to the nature of observational cosmology. We do not see the universe as it is now, but as it was, with the lag increasing the farther we look. The Andromeda Galaxy, our nearest large galactic neighbor, appears to us as it was 2.5 million years ago, the time it took for light to cross the distance between us. A galaxy at a distance of 1 billion light-years appears as it was 1 billion years ago, when the Earth was still forming and the solar system was young. A galaxy at z=10 appears as it was more than 13 billion years ago, when the universe itself was in its infancy. This means that our view of the cosmos is inherently fragmented across time. We see nearby objects in their relatively recent past and distant objects in their deep past, but we never see everything at once as it exists in a single moment. The present state of the distant universe is unknowable to us, hidden beyond the light travel time that separates us from it, and it will remain unknowable unless and until the light from that epoch reaches us billions of years from now. This creates a peculiar kind of knowledge, one that is rich in detail about the past, but necessarily incomplete about the present. We can map the history of the universe with remarkable precision, observing galaxies at a range of redshifts and thereby constructing a timeline of cosmic evolution from the earliest epochs to the present day. But we cannot observe the current state of those early galaxies, cannot see what they have become, cannot follow their individual trajectories through time except by inference and statistical analysis. We observe many galaxies at many different epochs, and from these observations we build models that describe typical evolutionary pathways. But the fate of any particular high redshift galaxy remains unknown. It is somewhere out there in the universe, existing in the present moment, but so far away that its current light will not reach us for billions of years, and by the time it does, we will not be here to observe it. There is something both humbling and clarifying about this constraint. It reminds us that our knowledge of the universe is always mediated by the finite speed of light and the vast distances involved, that we are observers looking backward through time, reconstructing history from the light that has managed to cross the void and reach our instruments. The early universe is not a place we can visit in any sense, not physically, not even through real-time observation, but only a past that we can glimpse through the ancient light that carries its image to us. And yet from this light, from these faint spectra and images, we can infer an extraordinary amount. We can determine the masses of stars, the rates at which they were forming, the chemical composition of the gas from which they formed, the gravitational environment in which the galaxies existed, the overall density and expansion rate of the universe at that time. We can reconstruct with quantifiable uncertainty the conditions and processes that governed that epoch, even though we can never witness it directly or interact with it in any way. The galaxies Webb observes are not merely distant in space, but distant in time, inhabitants of an era closer to the beginning of the universe than to the present, and the challenge of understanding them is as much about understanding time itself, how structures evolve, how matter organizes, how complexity emerges from simplicity, as it is about understanding galaxies. The question is not just what these galaxies were, but how they came to be so quickly, and what their existence tells us about the nature of the early universe and the processes that operated within it. The presence of massive galaxies in the early universe raises questions that extend beyond the galaxies themselves, touching on aspects of cosmic evolution that remain poorly understood. One of these is the relationship between early galaxies and the supermassive black holes that are thought to reside at their centers. Nearly every large galaxy in the present-day universe harbors a supermassive black hole at its core, with masses ranging from millions to billions of times the mass of the Sun. These black holes appear to have grown in tandem with their host galaxies, maintaining a rough correlation between the mass of the black hole and the mass of the galaxy's central bulge. But how and when these black holes formed, and how they grew so massive so quickly, remains uncertain. Webb has detected quasars, extremely luminous objects powered by actively accreting supermassive black holes, at redshifts above Z=6, indicating that black holes with masses exceeding 1 billion solar masses already existed when the universe was less than 1 billion years old. The presence of massive galaxies at even higher redshifts suggests that the formation of supermassive black holes might have been even more rapid than previously thought, or that they formed through mechanisms that allowed them to bypass the slower processes of accumulation through successive mergers and accretion. The standard picture of black hole growth involves the collapse of massive stars into stellar mass black holes, which then grow over time by accreting gas or by merging with other black holes. But this process is limited by the rate at which black holes can accrete matter. There is a maximum rate known as the Eddington limit, beyond which the radiation pressure from the infalling matter becomes strong enough to blow away additional material, preventing further accretion. Growing 1 billion solar mass black hole from a stellar mass seed through accretion at the Eddington limit would take hundreds of millions of years, which is barely enough time given the age of the universe when these quasars are observed. This has led researchers to consider alternative pathways, such as the direct collapse of massive gas clouds into black holes with initial masses of tens of thousands or even hundreds of thousands of solar masses, bypassing the stellar phase entirely. If such direct collapse black holes formed in the early universe, they could serve as more massive seeds that could reach billion solar mass scales more quickly. The connection between these black holes and the massive early galaxies observed by Webb is an active area of investigation, with researchers exploring whether the same conditions that allowed for rapid galaxy assembly might also have facilitated the rapid growth of supermassive black holes. Another open question concerns the role of these early galaxies in the reionization of the universe. Reionization was a fundamental phase transition in cosmic history, the process by which the neutral hydrogen filling space was ionized by ultraviolet radiation from the first stars and galaxies, rendering the universe transparent to light. The timing and sources of reionization are not fully understood. Observations of the cosmic microwave background and of quasars at high redshifts suggest that reionization was largely complete by around Z=6, corresponding to roughly 1 billion years after the Big Bang, but the process likely began earlier and proceeded gradually, with some regions ionizing before others. The massive early galaxies observed by Webb, with their high rates of star formation and large populations of young, massive stars, would have been significant sources of ionizing radiation. Determining how much these galaxies contributed to reionization and whether they were the dominant sources or merely one component among many requires understanding not only how many such galaxies existed, but also how efficiently the ionizing radiation they produced could escape into the surrounding intergalactic medium. Stars produce ionizing photons, but much of this radiation can be absorbed by the gas within the galaxy itself before it escapes. The fraction that escapes, known as the escape fraction, depends on the density and distribution of gas in the galaxy and is difficult to measure directly, particularly for distant objects. There is also the question of how representative the galaxies Webb has observed are of the overall population of early galaxies. The massive galaxies that have captured attention are by definition the most luminous and therefore the easiest to detect at high redshifts. But they may not be typical. For every massive early galaxy, there might be many more smaller, fainter galaxies that Webb has not yet detected, either because they are below the telescope's sensitivity threshold or because they have not yet been searched for in the data. Understanding the full population of early galaxies, their range of masses, their distribution across space, their star formation histories, is essential for building a complete picture of how structure formed in the first billion years. Ongoing surveys with Webb are working to address this by observing larger areas of sky and pushing to fainter detection limits, but the task is challenging and time-consuming, requiring thousands of hours of telescope time and careful analysis of vast quantities of data. Each of these questions, the formation of supermassive black holes, the sources and timeline of reionization, the completeness of the galaxy census, is interconnected, and answering any one of them provides constraints on the others, gradually building a more coherent picture of the early universe, even as individual pieces of the puzzle remain uncertain. The light from those distant galaxies continues to arrive, photon by photon, carrying information across a span of time so vast that it encompasses nearly the entire history of the cosmos. Each observation adds another point of data, another constraint on the possible, another glimpse into an epoch that exists for us only as ancient light. The galaxies themselves have moved on, evolved, merged, or faded, but the image they sent into space billions of years ago travels still, reaching us now, here, in this present moment, as if time itself were folded in ways that allow us to witness the distant past while standing in the present. What Webb has revealed is not an answer but a question made visible, a discrepancy between expectation and observation that signals something we had not fully understood. The early universe, it seems, was already organizing itself into complex structures, at a time when our models suggested such structures should not yet exist. Whether this indicates that galaxies formed more efficiently than we thought, or that the conditions of the early universe were different in ways we have not accounted for, or that our understanding of dark matter and gravity on these scales requires refinement, remains to be seen. The work of determining which of these possibilities is closest to the truth is ongoing, unfolding through observations that will take years to complete and models that will be refined and tested against an ever-growing body of data. There is no urgency to resolve this immediately, no crisis in the discrepancy. The universe does not demand that we understand it according to a schedule. It simply is, and it was, and the light from what it was reaches us whenever it reaches us, offering what information it carries. We build instruments to gather that light, we develop theories to interpret it, and we adjust our understanding as the observations require, knowing that each adjustment brings us closer to a description that matches reality, even if that description will always be incomplete, always provisional, always subject to revision as new observations extend our reach further into space and deeper into time. The early universe remains, in many ways, beyond our direct grasp. We see it only through the intermediary of light, only through the distortions of redshift and cosmic expansion, only through the models we construct to translate wavelengths and spectra into masses, distances, and ages. But from this indirect knowledge, this light gathered across billions of years, we can begin to piece together what those early epochs were like, how dense, how hot, how rapidly stars formed, how quickly galaxies assembled. We can trace the outlines of processes that operated when the universe was young, even if the details remain uncertain, even if the full story has not yet been told. The massive galaxies at z equals 10, at z equals 12, at z equals 13 exist in our data now, confirmed through careful measurement, their light analyzed and their properties estimated. They are real, these early giants, and their presence is a fact that the models must now accommodate. How they came to be, how the universe managed to build such structures so quickly, is the question that remains open, the mystery that invites continued investigation, the boundary where our current understanding meets what we have yet to learn. We thought we knew the timeline, the pace at which galaxies would grow, the gradual assembly over billions of years. What we are finding is that the universe was perhaps more capable, more efficient, more surprising than we anticipated. And in that surprise, there is an invitation not to certainty, but to deeper inquiry, to the recognition that the cosmos contains more complexity than any model will fully capture, and that the process of understanding is one without end. If this journey brought you a sense of calm, you can subscribe to Quiet Science and continue exploring these silent depths with us.